The cantilever beam that's shown here is loaded with by this constant line load P naught between points B and C. What we're asked to find here is the deflection curve for the beam under the action of that load. So the first thing we're going to do is look for our external reactions. For this, we'll draw a free body diagram of the complete beam. And one thing I will say before I start is I'm going to let the symbol A represent the length there of L over 2. So every place there is an L over 2, I'm going to put an A. At point A, we have a reaction force AY. We have a couple MA. And then we, of course, have over the line load, we have a value there of P naught times A. When I write down my moment equation about A, what I get is minus MA. I have P naught times A, that's the force. Its moment arm is going to be 3A over 2. It's going to be the complete distance of A and then halfway over between B and C. That's going to be a plus contribution. And therefore, from this, we see that at the wall, we have a bending moment being exerted on the beam, which is equal to 3/2 P naught times A squared. And then, of course, when I sum forces in Y, what I have here is AY plus P naught times A. Therefore, for equilibrium, we see that AY is equal to minus P naught A. So we're going to break this beam up into two parts. We're going to look at section AB. We'll draw a free body diagram of a piece of that beam where there's been a cut made somewhere between A and B. So here's the overall beam, and then there's going to be a cut made at this position of X. There will be the reaction force, of course, there of AY, the couple of the wall MA, both of which we've already found. We have the shear force, and we have the bending moment M, which is what we're trying to find. So I'm going to call this point D. So whenever I sum my moments about D, I get minus MA. This is the reaction from the wall. I have AY. It's got a moment arm of X. It's going to be in the minus Z. And then the internal bending moment there of M. So therefore, the internal bending moment for the beam then is going to be equal to MA plus AYX. And we've already found MA, so that's 3/2 P naught A squared. And AY is minus P naught A, then that gets multiplied by X. So that puts us in a good position because now we can write down our equation for the slope of the deflection of the beam. That's going to be theta x is equal to what it is at the wall plus 1 over EI integral from 0 to x of m of x, and that's 3/2 P naught A squared minus P naught AX. The wall, that doesn't allow any rotation. A clamp condition makes theta equal to a 0. I do the integration here, so I get 3/2 P naught A squared X minus, in this case, 1/2 P naught AX squared, like that. And then, of course, the deflection is going to be what it is on the left side, plus the integral of theta over that range, so that's 1 over EI, 3/2 P naught A squared X minus 1/2 P naught A X squared dx. The wall prevents a displacement, so that's a 0. I have 1 over EI, 3/2 P naught a squared. So the integral there of x is going to give us an x squared over 2 minus 1/3, so that in the outside is a 1/6 p naught a x cubed. So two things I'm going to write down. One is the slope of the deflection there at b. That's theta evaluated at x equal to a. So that's going to be 1 over ei, 3 halves p naught a squared times x equal to a minus 1/2 p naught a squared. So that gives us a value there of p naught a cubed over ei. 3 halves minus a half there gives us 1. So the deflection at b, we'll use both of these a little later on in the second half, where VB is V evaluated at A, so that's going to be 1 over EI, 3 halves P naught A squared. This should be a 3/4 there because I hadn't multiplied this out before. 3/4 P naught A squared times A squared again, so that's going to be to the 4th. Or cubed, I'm sorry. Messing up here. Oh. My mistake was in thinking I'd made a mistake. This truly was a to the 4th. And then this is minus a 6th p naught a to the 4th. So our deflection there at B is 7/12 p naught a to the 4th divided by EI. So these are two pieces of information we'll need later on in order to do our integration there between B and C. So now when I look at segment BC, I'll draw a free body diagram of the left half of the beam when I make a cut somewhere between B and C. This cut I denote as being at X location. I've got AY and MA with two reactions that I found at the beginning of the problem. And then we have the load which goes on there. This is going to be a P naught times the base there, which is x minus a. And the distance from there to there is going to be, well, I guess I don't want to do that, because what I'm going to do is do a moment there about E, where I've got a shear force V and a bending moment there of M. So what I want to actually designate is this distance here, and that distance is going to be x minus a divided by 2. It's halfway in between. When I sum my moments about E to write down my equilibrium equation for this, I get M. I have AY. It has a moment arm of x. And then I have P naught x minus a, that's my force. And then my moment arm is x minus a over 2. For equilibrium, that's a 0. So the bending moment in that section there between B and C as a function of x is AYX minus a half a P naught times x squared minus 2AX plus a squared. And when I put in my value for AY in combined terms, I end up with minus 1/2 P naught a squared minus 1/2 P naught x squared. So that's great, because now what we do is, to find the rotation of deflection between B and C, I'll use the integration of m to give us that rotation. So that's going to be minus 1 half p naught a squared minus 1 half p naught x squared. Again, that's integrated over x. This theta at 0, and I've made two blunders here. I'm doing my integration not from the left side, but I'm picking it up at x equal to a. So this is theta at a, which is what I put the shorthand notation in there for theta b. And then the integration from a to x, that's going to give me a minus 1 half p naught a squared. That's a constant in front. It's going to be x minus a. And then I have minus 1 half, and then the integral x squared is going to give me a 1 over 3. So this is minus 1/6 p naught x cubed minus a cubed, like that. So when I expand and I group together my terms, what this in bracket ends up being is 2/3 p naught a cubed minus a half p naught a squared x minus 1/6 p naught x cubed. I integrate that one more time. To find the deflection, I start out with the deflection at the left end of the integral, integrate from a to x, the value of ei, the function ei, 1 over ei, 2/3 p naught a cubed minus 1 half p naught a squared x minus 1/6 p naught x cubed. And I left off my theta b term, so let's not forget that one. So what I get here is that v of a is equal to vb. We found that above. And the integral of theta b, that gets multiplied by x minus a. And then I have 1 over ei, 2/3 p naught a cubed x minus a minus 1/4 p naught a squared x squared minus a squared minus 1 over 24 p naught x to the fourth minus a to the fourth. And so recall that above we found that VB was equal to 7/12 P naught a to the fourth divided by EI. Theta B is equal to P naught a cubed divided by EI. So that gives us our expression for the deflection. And keep in mind that I simplified things just a bit by letting A be representing their L over 2. So every place there's an A put in an L over 2. So that gives us our deflection of the cantilever beam with a constant distributed load on the right half of that beam. How did we do this? Well, the same thing. We find our external reactions first. In this case, we had the reactions at the wall, which was a couple MA, a reaction force AY. With that information, then we broke it up into two parts, AB and BC. We found the bending moment between A and B using equilibrium. We integrate that twice to get the displacement. We were able to enforce the no displacement, no rotation boundary condition there on the left hand side. And then we looked at B to C. We used equilibrium to find the bending moment. We did an integration of that twice to get the deflection, and we used information about theta and V there at B from our previous result. And that gave us the answer that's shown here.